This section deals with only a couple of theorems, but they each have 3 cases, so it will seem longer than it would initially seem. First, a few vocabulary items though. Seeing this word for the first time, people often don't know how to pronounce it, but it's secant. Now before we had tangent lines. Tangent lines only touched a circle at a single point. But if we move the lines in a little bit, then the lines now cross our circle in 2 spots. Now instead of tangent lines, we have secant lines. Secant lines intersect a circle in 2 spots. A secant ray intersects a circle in 2 spots. It doesn't matter if the endpoint is on the edge of the circle, like this red one, or whether the endpoint is outside of the circle, like this blue one. As long as the ray eventually crosses the circle in 2 spots, it counts as a secant ray. Next is a secant segment, which is a line segment that intersects the circle in 2 spots and has at least one endpoint outside of the circle. So this red one is a secant segment. Both of its endpoints are outside of the circle. This blue one is also a secant segment. It has one endpoint on the edge of the circle and one endpoint outside of the circle. However, this green one is not a secant segment. It does cross in 2 spots, but both of its endpoints are on the edge of the circle, so it is a chord, not a secant segment. In summary, it doesn't matter which type of secant you have, the secant must cross the circle in 2 spots, and at least some part of it must be outside of the circle. Now we have measures of angles floating in the middle. What does that really mean? Well, there are 3 cases for measures of angles inside of a circle. You must know all 3. You must keep them straight. We started off with a central angle which had its vertex at the center of the circle. We said that central angles were equal to their intercepted arc. Then we moved on to angles with their vertices at the edge. There were 2 types. One was an inscribed angle, and one was formed by a tangent and a chord. In either case, the measure of those angles is half of their intercepted arcs. If we have an angle inside of the circle whose vertex isn't at the edge and isn't at the center, then it has to be something like this. This is what I mean by an angle floating somewhere in the middle. Now we just need to figure out how their measure compares to the intercepted arc. But those are the 3 types of angles that are inside of the circle. In this angle that I have floating here, I have one angle and one intercepted arc. But for these angles floating in the middle, you actually have to extend out the sides so that they are both chords, like this. By creating these chords, you end up with vertical angles. This pair of vertical angles doesn't just intercept one arc, they intercept 2 arcs. We have transformed the picture to what we need. We started with one angle floating somewhere in the middle, but to talk about what its measure is, we need to have a picture like this. The theorem says that the measure of an angle formed by 2 chords that intersect inside of a circle is half the sum of the measures of the intersected arc. It is probably clearer in formula form, but the way most students seem to like to remember it is, as the measurement of the angle is the average of the 2 intercepted arcs. Remember it how you like, but in this situation we have 2 intercepted arcs, not 1, and the angle measure is the average of these 2 arcs. Now we move on to angles outside of a circle. First, if an angle doesn't touch a circle at all, like this blue one here, then that is useless. The angle and the circle don't relate at all, and we can't say anything useful about them. So that is not what we are talking about. Similarly, if we have an angle where only one side touches a circle, one part of the angle is a secant ray, but the angle as a whole doesn't relate to the circle. It is similarly useless for our discussion here. When we talk about angles outside of a circle, both of the sides of the angle must touch the circle. There are 3 possible ways for us to have an angle outside of a circle with both sides intersecting the circle. I could have an angle formed by 2 secant rays. I could have an angle formed by 1 tangent and 1 secant ray. I could have an angle formed by 2 tangents. These are the 3 possibilities. But even though there are 3 possibilities, the good news is that they all work exactly the same. In each of these cases, our angle ends up intersecting 2 arcs. One arc, the red one, is farther away from our vertex and larger. The other arc, the blue one, is closer to our vertex and smaller. It works the same for all 3 cases. Time to label all of these pieces. With these pieces labeled, we can now give you the formula. Central angles are equal to its intercepted arc. Inscribed angles are equal to half their intercepted arc. Angles floating in the middle are the average of the 2 intercepted arcs. And here we have 2 intercepted arcs too, but instead of the average, we have the measure of our angle is the difference of our 2 intercepted arcs divided by 2. I have had quite a few students prefer to think about it like this: the far arc minus the close arc divided by 2. If you like that better, then by all means remember it that way. The one thing to be careful of is, don't get it confused with the floating in the middle angle. That was 2 arcs added together and then divided by 2, but here you subtract them before dividing by 2. It is a very easy, and a very common, mistake that students make. Now to the last theorem. Over the course of this year, I have occasionally lamented how some theorems are written in such dense math speak that most people can't understand them, and certainly not a high school geometry student. But this one takes the cake. This one is a doozy. Don't even bother writing it down. it doesn't mean anything to 99% of the people out there. It is just a paragraph of confusion. Good grief. This bundle of crappiness leads us to 3 possible cases that you do have to know, but explaining it to you will work much better with pictures compared to words. The first case is when you have 2 chords crossing in a circle. When the 2 chords cross, they chop each other up into 2 segments. So there are 4 line segments now. I'll label them now. The thing you need to know is that in a case like this, A times B is equal to C times D. By far the most common error students make here is to add instead of multiply. So highlight that multiplication in your notes or something. It's the error to avoid. For our second case, we have these 2 secant segments. For these 2 segments, we look at these 4 pieces. Make sure you understand which 4 pieces we are talking about here. For each secant segment, it is the little piece outside of the circle and the whole secant segment. If you don't get which 4 pieces we mean, rewind and watch again before moving on. I'll go ahead and label the pieces now so we can give you the formula. With these pieces now labeled, we know that Q times the whole segment, Q plus R, is equal to S times the whole segment, S plus T. It is similar to the first case. You multiply the pieces together. For the last case, we have 1 secant segment and 1 tangent segment. I won't bother to run through another animation again, but for the red segment, just like the second case, we want to look at the little piece outside of the circle and the whole piece. Time to label my picture for the third case. With these labeled like this, we know that the little red piece outside of the circle, X, multiplied by the whole segment, x plus y, is equal to the tangent segment, z, squared. For all 3 cases, 2 things are multiplied together on each side of the equal sign, so that in the last case, z gets multiplied by itself. So that convoluted theorem that confuses even the best students leads to these 3 cases. These are the 3 formulas you will need to be able to deal with as you work through problems from this section.